Okay, this is recording. So we're going to start with some announcements. Let's see. This is Shobi. You always need to be checking in Shobi. But there was nothing new in Test 1 My Stat Lab questions or Test 1 notes in PowerPoint. But I have a bonus that's due tomorrow about midnight. It's a Bambi worksheet. It's kind of like the Disney movies worksheet. Worth 10 bonus classwork points. So if you have a low classwork grade, and I realize I can fix classwork grade, all your classwork grades. Okay. That's, you should, and how many of you have discovered the Learning Center? Well, the Learning Center, they come in here, they're right across the hall, right the way and downstairs. They are great. Go get help. Just because this is a bonus doesn't mean you can't get help with it. Okay, get help with it, or get help with the tutors that in various places. There's a bonus here, Chapter 3 review. It's just like the Manatee worksheet, sort of. So, that's, and it's either due tomorrow, though. I mean, we're going on to Chapter 4. Test bonus, Test 1 bonus. It's here. So, here's the Test 1 bonus. This is our actual class data with some, you know, I want you need to show your work. Oh, well, on 1 and 2 and 3, you don't need to show your work. You're supposed to work separately on this because this is a bonus test points. And then it's got the second page, too. So this was the actual daily average versus Test 1 grade. Wink, wink, yeah. But I did this at 10 o'clock last night. So anyway, that's what happens. And what you're supposed to do is go ahead and use whatever I typed in for your classwork average, even though everybody's going to be slightly off, okay? You're supposed to just put your daily average in here and you're predicting your test grade. And then you're supposed to take your actual test grade minus your predicted grade and divide it by your actual test grade times 100. So you're supposed to follow that formula. And I said to look ahead in chapter 10, so look at your book. Anyway, that's the Test 1 bonus. So, in D2L, I haven't opened it up yet because I haven't computed your grades. But I'll be computing your grades, and I'll be fixing it after I get some sleep. No. 15:30, there we go. I'll be fixing your grades after I get some sleep. I will post your grades so far, and then I will open up a quiz, but I'll give you a few days, a week or so to do it. I'm going to open up a survey that says self-evaluation after exam 1. It's a survey, and it won't be due, it'll be due, I'll give you all next week. It's very easy. You just take the survey, look at your grades, take the survey, and then ignore the grade it gives you. I'm going to change it to 10 out of 10. It's a survey. So no matter what you enter on that, as long as you do it, you're going to get a 10 out of 10 on that assignment. But I'll remind you about it Tuesday, too, or I'll type it into the Shobi to remind you. All right, so that's the announcements. We are on, let's see. Let me get the roll taken. And then we're on chapter 4. So let's open that up. chapter 4. But I gotta take roll. Pause it. Oh, there it is. Slideshow from beginning. Okay, this is not part of your notes to fill in, so if you want to take any notes from this slideshow or just go back into Tegrity, this is kind of the background to probability. You need to know the definition of the logical or, so, and. So this is kind of a silly slideshow. Here's Rita. There's Rita, okay? Have you all met Rita? She's, anyway. Are these statements true or false? Is Rita playing the violin and soccer? That's false. This seems kind of silly, but you guys got that, but it is false. You are correct. Is Rita playing the violin or playing soccer? Is that true or false? You got it.
It's true.
That's right. That's right. Okay. It sounds like we got a freight train. Okay. So, and means that both must be true. Both things have to be true for a logical and. And when we're talking about the English language, when we use the word and in the English language, a lot of times we mean or, logical or. So that's why we go through this. And means both must be true. Or means one or the other, or both are true. So this is just the background, and these are extra PowerPoints. They're posted in D2L. So this is Johnson City, right, where Elm and Maple cross. No, they probably don't even cross. But there's an Elm Street and Maple Street. There are tree streets down there, but they probably go in the same way or something. But so which one of these is Elm and Maple? The one on the right or the left? The one on the left is true. Elm and Maple both have to be true. The only way both are true is if you're standing in the intersection, you're both on Maple Street and Elm Street. But if you're standing here, you're only on Maple Street. If you're standing here, you're only on Elm. So this is why I go through the slideshow, because if you don't get and or, you're going to really struggle with probability. So which, now can you tell me which one's Elm or Maple? The one on the right. One or the other or both must be true. So Elm and Maple, and Elm or Maple, and Elm and Maple, this is called an intersection, and you can remember it because it's like when two streets cross. And at the back you probably can't see this, but it's like when two streets cross. Okay? So and is called an intersection, and both have to be true. And if you can think of this example to help you, like an intersection of two streets, you know, okay? Or is called a union, and you guys can all groan on this one. Like when you put the north and the south together, and you in the back probably can't see it, but okay, boo. We still have any Confederates in here? You don't want to be together? Anybody have a Confederate flag on their truck? No, it's all right. All right. So, or is a union, and one or the other or both are true. So, the next thing is just showing you about Venn diagrams. In a Venn diagram, the box represents the entire sample space. Okay? So, this circle represents that members that fit into event A go in that circle. And this circle means that members that go into event B go into this circle. So which is A and B? That is correct. It's the intersection where both are true. That's and. You got it. Which of this is, you're going to get this one, A or B? The one on the right here. And is called an intersection, and or is called a union. Okay. Okay. And the addition rule for probability uses this. We're going to stop there. We're going to, so. Okay, so we're going to start covering chapter 4 here. We've got probability now. And hopefully everybody's printing these notes out now. So when we're talking about probability, we can do an event, like we can roll a fair six-sided die once. So an event is, a procedure, sorry. I've got an earpod for this. A procedure is rolling a six-sided die once. And when we roll that die once, before we know what it landed on, the sample space is all the outcomes, or the simple outcomes. Let's see. Okay, we were going to do a procedure like rolling a six-sided die once. I have a Nearpod, but I'm just going to show you this slide. So again, it's going to show, and I'll have to move it up for the people in the back. We got a procedure. Maybe I should do the Nearpod. I don't remember. I don't think it starts here though. We got a procedure. For instance, just one thing it could be. You could be picking a card out of a 52-card deck of cards. So, events and sample space. An event is any collection of results or outcomes of a procedure. So I could let capital E mean that you're going to roll an even number. That's an event. Rolling an even number. A simple event is something that can't be broken down further. So if you roll an even number, that's rolling a 2, 4, or a 6. Okay? So rolling an even number is not a simple event. Rolling a 1, getting a 1 on a die would be a simple event. Sample space is all the possible simple events. So, that's like all the possible simple events for rolling a six-sided die that has the numbers 1 through 6 are 1, 2, 3, 4, 5, or 6. That's the whole sample space. The probability of the whole sample space, capital S here, is always 1. This is probabilities. We haven't started the notes yet, but okay. Notation for probabilities. Capital P denotes a probability. Some capital letters could denote specific events. I chose capital E for even, because that helps me remember I'm talking about even numbers. Probability, this means probability of event A occurring. That's our notation for it. So, for example, if you flip a coin, what's the probability it lands on heads? The notation for that is P of H, because we're going to use H to represent the coin landing on heads. And so what would that be? You'd have, on a fair coin, you'd have 1 chance out of 2, or 0.5. We're going to write our probabilities as decimals. And this is just the notation. So I'm going to go ahead and start a Nearpod for what we're covering then. Go into Nearpod. Nearpod. And my Nearpod. My library. Where's that? Chapter 4, probability. Let's just... Okay, so you go to nearpod.com and you enter K, G, U, O, F. And I'm just going to run it from here, so I'm going to hide, show student names or hide them. I'll have to figure out which one's which. Hiding is probably the I crossed out, so I think that's it. Okay, so everybody enter that. This is probability, chapter 4. Oh, so I do have the definitions of the events here in sample space, but it doesn't show the example of rolling a six-sided die once. So these are the definitions of events. You don't have, and sample space. You don't have to memorize these exact definitions. You know how to use them. So, and here's a notation. We already talked about this one. So you will have to put your probability notation on things. Okay, so here we are in the notes. If one event can occur m ways and the second event can occur in n ways, the number of ways the two events can occur is m times n. This is the fundamental counting principle, or they changed its name. I thought I fixed that. It used to be called the fundamental counting principle. Now our book calls it the multiplication counting principle, to tell you that you're going to multiply. So that's why your notes say multiplication counting principle, but the slide shows that. I may have fixed it, but I don't know. If I fix something, don't delete the old one. I don't know. Okay, so in a tree diagram, so we're going to do some examples on our note sheet. A tree diagram is just a picture of the possibilities, but they get big fast. So I'll do the examples on our note sheet now. So if you're going to roll 2 fair 6-sided die, how many rolls are possible when you're rolling 2 6-sided die? We're talking about 6-sided die here. How many rolls? We could make a whole chart with this, and this might be in the book, where you have 1 through 6, the possibilities on the one die, and then you're going to have 1 through 6 on the other die. And they might even, these are all the possibilities, and it's not a tree diagram, they might even draw a picture like 1 and 1, you know. But anyway, I'll just add these together. Different color. Oh, here we go. So I'm going to add these together. This would be 2, this would be 3, 4, 5, 6, 7. If you add 2, you could get a 2 on this die and a 3 on this one. Whatever it is. It's hiding. Okay. You could get a 2 on this die and a 3 on this one. That would give you a 5. And if you keep filling that out, so you only have one way to roll a 1 and a 1, or 2. Six, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. Leave it. Okay. There's only one way to roll boxcars, right? 2 6s. Okay. 2 6s. There's only one way to roll those. So you could use this. If you want to know the probability of rolling a 6 on 2 fair 6-sided die, it's the number of ways that you could roll a 6, 1, 2, 3, 4, 5 ways, out of 1, 2, 3, 4, 5, 6, out of 36 equally likely ways. So or you could just count those up. You don't have to draw this, though. We can use the fundamental counting principle to figure out that there's 36 equally likely simple events. 36. What you do, did you finish writing this down? Okay. How many rolls are possible when you roll 2 dice? Instead of looking at the whole situation and making a whole big chart, all you have to do is I'm going to put a line for the first die times the second die. So how many rolls are possible on the first die? 6. How many possibilities on the second one? So 6 times 6 is 36. There's 36 possible rolls. Doesn't mean we get 36 different numbers, but we get 36 possible simple events or outcomes. So there's 36. And then if we wanted to find the probability of rolling a 6, we could start adding up how many ways there are to roll a 6. You could roll a 1 and a 5, a 2 and a 4, etc. You count them up. Or you make that big chart. All right. Okay, so the next example, simple. We've got a baseball manager that has 5 pitchers and 2 catchers. How many different possible pitcher-catcher combinations can he field? So we're going to make a line for the pitchers to put the number of possible pitchers there times the number of possible catchers. So that's 5 times 2 is 10. So we're counting the possibilities, not actually picking catcher A and catcher 2, or pitcher, whatever. Okay. All right, and then what if you're going on vacation and you don't care about style? And you have access to laundry facilities. And you've got 2 pairs of pants. What's that? You got 2 pairs of pants? What's that? 3 shirts and 2 pairs of socks. And you're not going to put a black sock with a white sock, okay? So how many different outfits, if you're going to pick 1 pair of pants, 1 shirt, and 1 pair of socks, you're just going to multiply these things. The pants, you got 2 of them. 3 shirts and 2 pairs of socks. 2 times 3 is 6, times 2 is 12. 12 different outfits. So, gosh, that's almost 2 weeks worth. All right. And let's see if it's the next, I gotta remember this. Here's the slideshow. Let's see if, oh, what was the quiz on? Oh, hide names. What's the quiz asking you about? Or do I need to keep, is it, oh, you guys not in this Nearpod? Oh, no, we can't do the quiz yet. Okay, get into the Nearpod. We'll do I'm going to back out of the quiz. I should keep going on my notes. I forgot how far I need to go. Oh no, I wanted to back out of the quiz here. We have to keep going on the notes. So, let me show you a tree diagram. A tree diagram is another way to figure out all the possible outcomes in simple events. So, if you're gonna do a tree diagram with this, if you're gonna pick your pants and you've got a black and a tan pair of pants, a B and T, and then you're gonna pick your shirts. You're gonna pick your shirts next. Red, R for red, sorry, W for white, Y for yellow. Red, white, yellow. And then if you're going to pick your socks, I'm running out of room. They're white and black. White, black, white, black, white, black. So you could write the sample space this way: black, red, white, black, white, red, sorry, black, black, W, W, black, W, B, that's black, white, black. You got the 2, then the black, yellow, white, and then we got the VYB there, and that's the first 6. Then you got all the ones that start with tan. And so you would have 12 outfits. But a tree diagram gets big fast. So I would have kept going. TRW, TRB, TWW, TWB, TYB, TYW, TYB. So I just got tired of writing them. Okay, so that's a tree diagram, and that's one way you can figure out probabilities. So, some more examples that we need to talk about here is if you have a security system for your house, and it's got a 4-digit access code. When we talk about digits, we mean the numbers, each digit can be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. When you're pressing the numbers, you guys have numbers, codes on your garage door maybe, or even to your car. You can't press the number 10, but there are 10 possible digits, because 1 through 9 is 9 and 0 is 10. So there's 10, each digit has 10 possibilities. Okay? So how many access codes are possible if each digit can only be used once? So you're going to press 4 numbers like 1, 1, 1, 1. But no, for this example, only you can use it at digit 1. You might be pressing 1, 2, 3, 4, and that might be your code. But we're not trying to guess the code. We're just saying how many possible codes are there. And we could start listing them. There could be 0, 1, 2, 3, 0, 1, 2, 0, 1, 2, 4, 0, 1, 2, 5. You take forever listing all those codes. Well, how long would it take? Well, how many access codes there are actually? Let's make this represent the first digit. And it's not a division sign. We're just making a line to put our second digit in, our third digit possibilities in our fourth. So remember, you're not guessing the codes, you're determining the number of possibilities. At the bottom it says that. So we can only use each digit once. So when we first how many possibilities before we press the first choose the first number? There's 10 possibilities, because there's 0 through 9. There's 10. Now suppose we pick the number 7. You can't use that number again. So we got to take 10 minus 1 possibilities is 9. We only have 9 possibilities. Once we've chosen a number for this one, we can't use it again, so we got to go down by 1. And then once we've chosen a number for here, we got to go down by 1, is 8. And 8 minus 1 is 7. So we're not saying the code is 10987. We're saying that on the first, when we're picking our code, we could pick 0 through 9 on the first digit. And count those out, there's 10. The second digit can be, and we have to cross out whatever we pick. It's got to be 1 less. So let's do that on the calculator. And it would take us forever if we started listing all the possible codes, because that's 10 times 9 times 8 times 7. Or 5,040 different codes. So we really don't want to list all the possibilities. No. Do we want to make a tree diagram with that? No. We'd have 10 branches. And then from each branch over here we'd have 9. And then 8, and then 7. Yeah. That's why we use the fundamental counting principle. It lets us look at each digit separately. Okay. All right, another access code question. Suppose it says how many access codes are possible if each digit can be used more than once, but the last digit cannot be a 0. Okay. So I'm going to write first, second, third, fourth here again. And this digit cannot be a 0. And the digits can be used more than once, means they can repeat. The digits can repeat. So so there's no restrictions on the first, second, and third digits. So we can program any number between 0 and 9 in there. And that's 10 possibilities. This last digit can't be a 0, so we gotta do 10 minus 1. You gotta take the 0 out of there, you're left with 9 possibilities. And then you multiply that out, and you get 9,000 different codes. So there's more codes if we allow the digits to repeat. Okay, and the next example, how many access codes are possible? And now I'm just going to make the lines, and it's saying the first digit cannot be a 5 or a 7, and the last digit has to be odd. And there's no restrictions on the second and third. So the first cannot be a 5, can't be a 7. So for the first digit, we take 10 minus 2 is 8. There's 8 possibilities, 0 through 4, 6, 8, and 9. Those are the possibilities. And then there's no restrictions on the middle digits, so those are 10s. Odd, for it to be odd, it has to be a 1, 3, 5, 7, or 9. That's 5 possibilities. So multiply that out, and you get 4,000 different codes. Okay? So I think now we can take that quiz. Alright, and I'm going to go into Nearpod and enter it too so I can look at the quiz. It's KGUOF. So you have to hit let's go. And the 0 is considered an even number. You have to hit submit. Let's see, and since I didn't answer, I still want to continue. If you hit this arrow, you're skipping the question. So if you're doing a Nearpod at home with a quiz, you always have to hit the bottom one and answer every question for participation points. Okay. There's 26 letters in the alphabet. And that's it. Okay. I'm going to submit my answers. I did really poorly on that, but we'll go back. And now I can share it. Now you can see you should be able to go back. You'll see the questions and the correct answers. So, did you understand what we just went over? All right, and it's about time. Let's take a break after this. Okay. You got 50%, right? All right, let's take a break.
How is it not working now? Because it's telling me it's 12 million. I got the same as your kids.
Oh.
8 times 10 times 10 times 10.
Oh, does it say I got that one wrong?
Yeah, because it's telling us it's 12 million.
Oh, it is saying.
Saying it's 12 million.
Oh, letters cannot be repeat. Whoops, I did it wrong.
Oh.
I forgot that part, so I got to change this to a 25 and a 24.
That makes sense.
Okay, so that's why it's the 12. It said the letters, the digits can repeat, but the letters cannot repeat. And I missed that when I read that, so it's important to read the things carefully. Read the questions carefully. And so what is that? Oh, that's a 12,000 number, right?
Yeah, it becomes 12 million after you go that way.
Okay, so I got 50% also on that. Because I didn't read it carefully. All right. We're going to pause this. This is called a draw it. So you're going to flip a coin and then draw and roll a die, a six-sided die. Draw a tree diagram to show the different possible outcomes. So on this computer, you can choose the pencil and choose whatever color you like. Or you can also choose text. So it's not going to be pretty, but okay. There's an eraser, so you can. And you can change the size of the eraser. You could also choose the text box and make it smaller, grab it, move it up here. and then you can type in like the 1, and you can choose the color, black. There we go. I probably didn't even answer all the questions. Okay. That's called a Draw It, and if you had an iPad, you could be drawing right on the iPad. I didn't finish the whole thing. No. Does it let me go back? No, doesn't let me go back. Oh, and then it says how many possible outcomes can occur, so you can answer that question. So, you can also choose the internet box and search for a picture. You can look at for pictures of it, but now you can't do it anymore. Or you could have drawn your picture on your paper, taken a picture with your phone, or there's all kinds of ways to do this. It's called a Draw It. It's a little hard to draw on a computer. And we don't have a million years for it, so, but, and then when I'm in here, you can see them all. Here they are, 12 outcomes, good job. At least these don't have names on them. It is kind of hard to draw a tree diagram with that. Oh, here somebody had a 4-sided die, I guess. And over here. And then there's a smiley face. Sometimes people just draw a picture. Okay. All right. And people are entering things. That's everybody's, and I can choose one and make it bigger and display it to everybody. So that's a tree diagram. This is good. Somebody wrote down all the outcomes. Here, can you see it? Probably not. As soon as I click on it, then you can't keep entering, so I don't want to click on it yet. So, usually my stats class is kind of like this kind of break and being able to just draw something, but this is called a Draw It. Is everybody done? Not quite. We gotta keep going. And it's not going to be graded. All right, we're gonna. You might just hit submit because I'm gonna display some now. And usually I could have an iPad and just pick, and you wouldn't see all these, but. Okay, so this person, and as soon as I hit share, then you have to see that one on your screen, right? No? That didn't work, right? Share. Now, does it show up on your screen? Yeah. There we go. So that's nice. Somebody showed all the outcomes. All right. Close that. Oh, and here's the smiley face. We always like smiley faces in this class. Okay. Even if they don't know the answer, we want a smiley face. No, there's somebody, just a smile. There we go. I'm dropping. Oh no. Well, okay, let's just play the name. No. I'm dropping. Oh. so sad. Somebody said hi. Okay. So you're enjoying this little thing. That's a draw it. Ah! Can you go back and take it? Yeah. Oh, okay. I'm dropping. Okay. All right, so this is the law of large numbers. In the long run, as the sample size increases, the relative frequencies of outcomes get closer and closer to the theoretical or classical probability value. There is a, I don't think it lets you do that. There's supposed to be a probability applet. Let me show you, I don't think these slides are in here. So that was the law of large numbers. Let me explain before you talk about that. I've already used this rule for finding, there's some basic rules for computing probability. The classical approach to probability, which I used when I was talking about probability of rolling, flipping a coin and getting 1/2. This requires equally likely outcomes, and I did it with finding probability of getting a 6 when you roll 2 die, 2 6-sided die. Well, as long as you have the number of different simple events is n, and that you can get that by the computer. Okay, so this is the classical or true approach to probability. It requires equally likely outcomes. So if you're going to roll a 6-sided die once, the probability of getting an even number, there's 3 even numbers, 2, 4, or 6, out of 6 possibilities, so it's 3/6 or 1/2. This is the true probability, but sometimes we don't know the number of, we don't know what n is. In that case, we use a relative frequency approximation, Relative frequency approximation is that we actually conduct or observe a procedure, and we'll do that next time with the beat activity, and count the number of times event A actually occurs. And based on these results, probability of A is approximated as follows. Probability of event A is the number of times we got that event over the total number of times we repeated the procedure. So those are the 2 basic ways that we do probability. And do I need to leave that up? Or you got it? Are you copying that? No. Okay. Okay. So back to the law of large numbers slide. So if you flip a fair coin, what's the true probability of it landing on head? 0.5 or 50%. We'll talk about it in decimals, but 0.5. But suppose you didn't know it was 0.5. This is the frequency approximation. If you actually flip the coin 20 times, n would be 20. And if you only got 8 heads, then you might think that the probability of getting heads on a coin would be 8/20 or 0.4. Well, the more and more times that if you repeat this experiment, say you flipped it 100 times or 1,000 times, you get closer and closer to the true probability of 0.5. And that's the law of large numbers, and that's what casinos use. So, and there's I don't know if the probability applet works. So that's the law of large numbers. I get an error. No, it's not finding that. This was an applet. There's probably other ones out there. Maybe it needs you to log in. Does it let me? No. Open and reload. It's not finding the, oh no. That didn't help. What happened to, oh, it's not found, okay. Well, there's an applet out there where you can estimate that. We need to, I got out of my thing. Let's see, join KGU. Well, let me keep going, or what's going on? Or is it over here? Whoops. Okay, I need to go back to my library and start it again. $15.30 probability. You guys all got kicked out, but you can go back into it. That's not working, so probability limit. This is so if you're rolling a six-sided die, and I'm gonna roll that die, and I want to know the probability of rolling a 7 on one roll. So we're gonna roll what's the probability if you're gonna roll a die once? That's a procedure. It's a six-sided die. What's the probability that you roll a 7? 0. You can't roll a 7. There's no 7s in one roll. You can't roll a 7. There's no 7s on this die. So I'm not talking about an 8-sided or 12-sided or something. Okay, we're rolling a 6-sided die. There's no 7s. All right, what if we are going to roll the 6-sided die and we want the probability that we roll a 1, a 2, a 3, a 4, a 5, or a 6? What's the probability that we roll one of these numbers? And so it'll be 1. We do it as a decimal. Yeah, 6 over 6, or 1. So this is a certain event. It's an event that's certain to occur. The event. This is an impossible event. So our probability limits, every probability has to be between 0 and 1. You can't have a negative probability. You can't have a probability more than 1. I don't know, it sounds like we're at a bowling alley. Is that what it is? Somebody's bowling? That's what it sounds like. Okay. Alright, so the probability of an impossible event is 0. The probability of an event that is certain to occur is 1. Complementary events. A complement is all the outcomes in which event A does not occur. The complement is shown as the letter with a bar over it. We say A bar. So probability of event A occurring plus probability of event A bar, or the complement occurring, equals exactly 1. That's the whole sample space. So we could solve for this, and this is the complement rule, 1 minus probability of A. So going back to our sheet, we're going to write those two. So the complement consists of all outcomes for which the probability of event A does not occur. The complement is denoted as A bar. If we're talking about event A, if we're talking about event B, it's B bar. A bar over whatever the event. We say A bar, like X bar. X is not a complement. It means not a complement. Okay, and the formulas are the probability event A plus probability event A bar. That's our whole sample space, so that equals 1. So if we had to, we could solve for this. We subtract probability of A from both sides. We get probability of A bar, or A complement, is 1 minus probability of A. So you're going to roll one die, and what's the probability that the die will not land on a 3? So I'm going to say probability of 3 bar, right? Not land on 3, I'm just going to call it 3 bar. Okay? One way we can find that is 1 minus the probability of it landing on 3. How many 3s are there on this die? 1. And how many equally likely outcomes? 6. So we can do that in our calculator. 1 minus the 6 is 5 6. But I can show you your calculator does this. You're allowed to use your calculator on the test. So you can do 1 minus 1 divided by 6, enter, and then you press math, and that's to fraction, enter, enter, and it does the fraction for you. So if you struggle with fractions, you can use the calculator. But it helps if you know fractions, though, to know if you got a reasonable answer. Okay, and the other thing is, well, how else could we have found this probability that it won't land on a 3? Well, probability that it won't land on a 3 means it could be 1, 2, 4, 5, or 6. And there's 5 ways that it doesn't land on a 3 out of 6 equally likely ways. And that's looking at the sample space. So you can look at the sample space to find probabilities, or you can use the complement rule like we did here, which also looked at the sample space for this one. Then the last example here is find the indicated complement. Sometimes we can't add up the sample space. We're going to just use this recent survey result. Says that 64% of all third graders bring their lunch to school each day. So, Family Feud survey says. All right, so find the complement of this. So if we're going to change percents to decimals, probability that they bring their lunch, P of L, will be 0.64. To change a percent to a decimal, we just divide by 100. What's the probability of the complement of that? We have to subtract from 1 is 0.36. Okay, how are we doing? All right, and we're going to talk about odds. And 1, we're gonna be talking about odds, and we'll talk about those. We'll be stopping pretty soon, let's see. Have we figured out why we have a bowling alley over there?
Idea.
Is it just people walking down the hall, or is that what is it? The wind blowing something or something? I don't know. Okay, your teacher got distracted. Okay. All right, so maybe you've heard of odds. Odds are a comparison of the probability of an event to the probability of its complement. So on your paper, you've got some ways that you can find find formulas for odds. In favor of event E is the probability of event E divided by the probability of E complement. Odds against an event E is going to be probability of event E complement divided by E. And we're going to do some examples. So here's some examples. So if there's 12 boys and 10 girls in a classroom, and we're going to reduce that, by the way, and we're going to use colon. We're going to use colon to show odds, but we will reduce and use a colon. So if there's 12 boys and 10 girls in a classroom, find the probability of choosing a girl. So P of G, for G, event G will be picking a girl. There are 10 girls, and you're picking at random, and there's how many students? 10 plus 12 is 22. And so that would be 5 over 11. That's probabilities. Find the odds of choosing a girl. The odds of choosing a girl would be, that's in favor of choosing a girl, would be probability of girl divided by probability of girl complement. But I do it this way instead. It's going to be, in favor is 4 and against. And then you have to reduce it because it is a fraction, even though we're writing it with a colon. So how many girls are in the classroom? 10. How many boys? 12. 4 and against. And then we reduce that. If you want it, you could do 10 divided by 12 in your calculator, or you can divide a 2 out of both of these. It's 5 to 6. That's your answer. So if you did it this way, it's a lot more complicated. It's 4 and against for odds in favor. For what are the odds of choosing a boy? The odds of choosing a boy, I'm not going to even write this. It's going to be, this is in favor of choosing a boy, would be 4 boy, and against would be 12 to 10, or divide each side by 2, you get 6 to 5. That's odds. Oh, you can't see that because it's, let me move this up. People in the back can't see. So it's 6 to 5. Did you get that? And these filled-in notes are out there on the website. Okay, and then the last, let's do these examples. So if you're picking beads out of a bag, find the probability of picking a blue bead. Let's let B, capital B mean blue, capital W for white, capital P for pink, capital Y for yellow. Find the probability of picking a blue bead is the number of blue beads out of the total number of beads in the bag. So we got to add these together, 10, 19. Find the odds though now in favor of drawing a blue bead. That's 4 blue, the ways you can pick a blue, and against picking a blue. So you'll have 3 ways to pick a blue and 19 minus 3 to not pick a blue. So that's 3 to 16. The odds in favor of picking a blue bead are 3 to 16, not 19. The odds against drawing a pink bead are against pink, colon, for pink. Can you see this? Against and for pink. So how many pink beads are there? 5. There's 19 total, so we have to subtract the 5. So that's 14 to 5, and that doesn't reduce. The 14's 2 times 7, and that 5's prime. Alright, find the probability. Now we want probability. So we use probability notation, not white. That's the complement of white. One way we can find that is probability is 1 minus the probability of picking a white bead. You'll have to practice this. Probability of picking a white bead. How many white beads are there? 7, and there's 19 total. So this is going to be, for probabilities, you use the total in the fraction. For odds, you have to, it's 4 and against, or against and 4, depending on this was against. So you do that on the calculator. 1 minus 7 divided by 19. Oops, turn it on. 1 minus 7 divided by 19. Math, enter, enter, and you get 12/19. Now find the odds in favor of drawing a blue or a white bead. Probability of drawing a blue or a white is the number of ways we can draw a blue or a white. There's 3 blue beads and 7 white beads over 19 is 10 over 19. Probability of drawing, no, that was odds, sorry. I didn't read it right. That's odds. It's 4 blue or white, there's 10 ways, and then we have to do 19 minus 10. So it's 10 to 9. And the last example for today, the probability, you gotta be careful. So this is the probability, we ask for odds. So probability of drawing a yellow bead is probability of yellow. How many yellow beads are there? 4 over 19. And we'll stop there.